Tonight on The Sleepy Scientist, we read drifting gently across the cosmic void to explore one of humanity's most profound questions. Is there life on Mars? From the red planet's ancient rivers to NASA's groundbreaking discoveries, we'll journey through the peaceful science of astrobiology and discover what the search for Martian life reveals about our place in the universe. In the quiet darkness above our heads, suspended in the velvet of space, a rusty world turns its ancient face toward our distant Earth. Mars, the red wanderer that has captivated human imagination for millennia, holds within its dusty plains and polar ice caps the potential answers to questions that have stirred our souls since we first gazed upward at the stars and wondered if we are alone. Tonight, as we embark on this gentle journey across the cosmic gulf that separates our blue world from that distant red one, we carry with us the accumulated wisdom of decades of robotic exploration, the careful observations of countless scientists, and the profound hope that life in whatever form it might take exists beyond the boundaries of our terrestrial home. The search for life on Mars represents more than scientific curiosity. It touches the deepest questions about our existence, our origins, and our destiny among the stars. If life arose independently on Mars, it would suggest that the universe teems with biological possibilities. If we find that Mars once harbored life, or still does in hidden corners, we discover that we are not alone in our cosmic neighborhood. As we prepare to explore this question with the peaceful thoroughness it deserves, we'll travel through time and space, from the earliest human observations of the red planet to the sophisticated rovers that now traverse its surface seeking signs of ancient or present life. We'll examine the evidence with the careful attention of scientists and the wonder of dreamers, understanding that each discovery brings us closer to answering one of humanity's most fundamental questions. In the quiet of this exploration, we'll discover that Mars has already revealed much about the possibility of life beyond Earth. The planet that once seemed impossibly alien has shown us ancient riverbeds, polar ice caps, and seasonal changes that speak of a world not entirely unlike our own. Recent discoveries of organic compounds, methane emissions, and subsurface water have transformed Mars from a dead, sterile world into a planet of possibilities. The story we'll tell tonight unfolds across billions of years, from the formation of Mars in the early solar system to the current moment, when robotic explorers search for biosignatures in Martian soil and rock. It's a story that encompasses geology and biology, chemistry and physics, engineering and exploration, all unified by the simple but profound question of whether life exists beyond our Earth. As we drift through this exploration together, we'll meet the scientists who dedicated their lives to understanding Mars, the engineers who built machines capable of surviving the journey to another world, and the visionaries who dared to imagine that life might exist in the cold, thin atmosphere of our planetary neighbor. Let us begin this gentle journey with minds open to wonder and hearts prepared for the possibility that we may not be alone. In the peaceful darkness of space, Mars continues its ancient dance around our shared sun, carrying within its rocks and ice the potential to transform our understanding of life itself. As we drift deeper into our cosmic journey, let us first acquaint ourselves with Mars itself, that mysterious red wanderer that has captured human imagination since our ancestors first noticed its distinctive rusty glow moving against the starry background of night. Understanding Mars as a world with its own geology, atmosphere, and seasons provides the peaceful foundation for understanding why scientists believe it might harbor life. Mars circles our sun at a distance of approximately 142 million miles, about half again as far from our star as Earth orbits. This greater distance means that Mars receives only about 43% of the sunlight that warms our world, creating a perpetually cold environment where even the warmest summer day at the equator rarely exceeds the freezing point of water. Yet this cold world maintains many Earth-like characteristics that make it the most potentially habitable planet in our solar system. The planet that reveals itself to our robotic explorers is a world of breathtaking landscapes and geological wonders. Olympus Mons, the largest volcano in the solar system, rises to a height of 13.6 miles above the surrounding plains, nearly 3 times the height of Mount Everest. The Vales Marineris, a canyon system that stretches over 2,500 miles across the Martian surface, dwarfs our Grand Canyon and speaks of geological forces that shaped this world over billions of years. Mars completes one rotation in just over 24 hours, giving it a day length remarkably similar to Earth's. Its axis is tilted at 25 degrees compared to Earth's 23.5 degrees, creating seasonal changes that astronomers can observe even from Earth as the polar ice caps advance and retreat with the Martian year. These familiar rhythms of day and night, summer and winter, create a world that feels somehow familiar despite its alien nature. The Martian atmosphere. Though thin less than 1%, the density of Earth's consists primarily of carbon dioxide, with traces of nitrogen, argon, and other gases. This tenuous atmosphere creates weather patterns including dust storms that can engulf the entire planet for months, as well as more gentle phenomena like clouds and morning frost. The atmospheric pressure at the Martian surface is roughly equivalent to what Earth's atmosphere would feel like at an altitude of 100,000 feet. Perhaps most intriguingly, Mars shows abundant evidence of water's past presence on its surface. Ancient river valleys carved through cratered highlands, delta formations spread across what were once lake beds, and mineral formations that could only have formed in the presence of liquid water dot the landscape. These geological signatures tell a story of a warmer, wetter Mars in the distant past conditions that might have supported life. The planet's surface bears the scars of a violent past, with impact craters covering much of the southern hemisphere, while the northern lowlands appear relatively smooth and young. This dichotomy between the ancient, heavily cratered south and the younger northern plains suggests a complex geological history, involving volcanism, impacts, and possibly even plate tectonics in Mars' distant past. Mars possesses two small, irregularly shaped moons, Phobos and Deimos, that are likely captured asteroids. Phobos, the larger and closer of the two orbits, so close to Mars that it completes 3 orbits in a single Martian day, appearing to rise in the west and set in the east, as seen from the planet's surface. These moons, while tiny compared to our own, add to the alien beauty of Martian skies. The red color that gives Mars its distinctive appearance comes from iron oxide rust in the planet's soil and rocks. This oxidation occurred over billions of years as iron in Martian rocks reacted with oxygen in the atmosphere, creating the rusty dust that coats much of the planet's surface. Interestingly, this process of oxidation might have consumed much of Mars' early atmosphere, contributing to the thin air that characterizes the planet today. Seasonal changes on Mars involve more than just temperature variations. The planet's elliptical orbit and axial tilt create complex seasonal patterns where the southern hemisphere experiences shorter, warmer summers and longer, colder winters than the north. During southern summer, dust storms are more likely to develop, sometimes growing to planetary scale and lasting for months. The Martian polar regions hold vast quantities of water ice mixed with frozen carbon dioxide. The northern polar cap contains enough water ice to cover the entire planet to a depth of about 35 feet if melted. These polar deposits represent one of Mars' largest known water reservoirs and play a crucial role in the planet's climate system and potential for hosting life. Recent discoveries have revealed that liquid water might still exist on Mars under certain conditions. Recurring slope-linear dark streaks that appear seasonally on steep slopes might indicate brief flows of briny water during warmer periods. The high salt content of this hypothetical water would lower its freezing point, allowing it to remain liquid at temperatures that would freeze pure water. The magnetic field of Mars differs dramatically from Earth's. While our planet maintains a strong global magnetic field generated by its molten core, Mars has only localized magnetic fields in certain regions, suggesting that it once had a global magnetic field that has since disappeared. This loss of magnetic protection has allowed the solar wind to gradually strip away much of Mars' atmosphere over billions of years. Understanding Mars as a complete world with its geology, atmosphere, climate, and history provides the essential context for asking whether life could have arisen there. The evidence for past water, the presence of organic compounds, and the potential for subsurface liquid water today all contribute to making Mars the most promising place in our solar system to search for life beyond Earth. As we prepare to explore humanity's growing understanding of this remarkable world, we carry with us the knowledge that Mars is not merely a distant alien planet, but a world with its own complex history, dynamic present, and the tantalizing possibility that it might harbor the greatest discovery in human history, proof that life exists beyond our precious blue planet. Let's float gently toward the realm of human imagination and scientific speculation, where for centuries, astronomers and dreamers have gazed at the red dot in the night sky and wondered about the possibility of life on Mars. These early dreams and theories, while often incorrect in their details, reflect humanity's deep longing to find companionship among the stars and our intuitive sense that life might not be unique to Earth. The story of imagined Martian life begins with the naked-eye observations of ancient astronomers, who named the wandering red star after Mars, the Roman god of war, for its distinctly blood-colored appearance. These early observers could never have imagined the detailed world that telescopes would later reveal, but they recognized something special about this particular celestial wanderer that set it apart from the other planets. The invention of the telescope in the early 1600s opened new windows into the Martian world. Galileo's early observations showed that Mars had phases like the Moon, confirming that it orbited the Sun rather than Earth. As telescopes improved over the following centuries, astronomers began to discern surface features, dark and light regions that seemed to change with the seasons, and brilliant white caps at the poles that grew and shrank in predictable cycles. In 1877, Italian astronomer Giovanni Schiaparelli made observations that would profoundly influence human perceptions of Mars for nearly a century. Through his telescope, he observed linear features on the Martian surface that he called canoi, Italian for channels, or grooves. When this word was translated into English as canals, it carried the unfortunate implication of artificial waterways, sparking decades of speculation about Martian engineering and civilization. American astronomer Percival Lowell became the most famous proponent of the idea that Mars was not only inhabited but home to an advanced civilization. From his observatory in Arizona, Lowell mapped hundreds of supposed canals crisscrossing the Martian surface. He theorized that these were massive irrigation works built by an intelligent Martian civilization, attempting to bring water from the polar ice caps to agricultural regions near the equator. Lowell's vision of Mars captured the public imagination like few scientific theories before or since. He described a dying world where an ancient civilization struggled against planetary desiccation, constructing vast engineering works to preserve their fading water resources. His writings painted Mars as a mirror of Earth's possible future, a cautionary tale about planetary environmental change and the lengths to which intelligent beings might go to preserve their world. The seasonal changes observed on Mars seemed to support the idea of plant life on the red planet. Dark regions appeared to spread during Martian spring and summer, leading many astronomers to conclude they were observing vast areas of vegetation, responding to seasonal warmth and the availability of water from melting polar caps. These observations, while ultimately incorrect, represented careful scientific reasoning based on the best available evidence. The spectroscope, which allowed astronomers to analyze the chemical composition of distant objects by examining their light, provided the first concrete evidence against a life-bearing Mars. Early spectroscopic observations showed that Mars had a very thin atmosphere, with little or no oxygen or water vapor conditions that seemed incompatible with life, as it was then understood. However, the technology of the time was not sensitive enough to detect trace amounts of these vital gases. Writers and visionaries seized upon the idea of Martian life, creating stories that reflected both scientific speculation and cultural anxieties of their time. H.G. Wells' The War of the Worlds presented Martians as technologically advanced but morally bankrupt beings who invaded Earth to escape their dying world. Edgar Rice Burroughs created a more romantic Mars populated by various humanoid species living in a world of adventure and conflict. The famous War of the Worlds radio broadcast by Orson Welles in 1938 demonstrated how deeply the idea of Martian life had penetrated popular consciousness. The realistic news bulletin format of the broadcast convinced many listeners that Mars had actually invaded Earth. showing that the possibility of Martian life felt real and immediate to many people. Despite the lack of concrete evidence, as telescopes improved and photographic techniques developed, the supposed canals of Mars began to fade from view. More detailed observations showed that what Lowell and others had interpreted as linear engineering works were actually optical illusions, the tendency of the human eye and brain to connect random features into linear patterns when observing at the limits of telescopic resolution. The advent of radio astronomy in the mid-20th century provided new tools for studying Mars. Scientists attempted to detect radio signals that might indicate technological civilization on Mars, but these searches revealed only the natural radio emissions expected from a geologically active planet. The dream of a technologically advanced Martian civilization gradually faded as more sophisticated observations failed to find supporting evidence, even as the romantic vision of canal-building Martians dissolved under scientific scrutiny. The possibility of simpler forms of Martian life remained viable. Astronomers and biologists began to consider whether Mars might harbor microorganisms or simple plant-like life forms adapted to the planet's harsh conditions. This more modest but scientifically grounded speculation laid the foundation for modern astrobiology. The seasonal changes that had been attributed to plant life were eventually explained by dust storms and wind patterns that redistributed the fine Martian soil, creating the appearance of spreading dark regions. While this explanation was less romantic than the idea of Martian vegetation, it demonstrated the dynamic nature of Mars' atmosphere and surface processes. The cultural impact of these early dreams of Martian life extended far beyond astronomy. They influenced literature, art, and popular culture, creating enduring archetypes of alien life and interplanetary conflict that continue to shape science fiction today. More importantly, they demonstrated humanity's deep desire to find life beyond Earth and our willingness to project that hope onto the most promising candidate in our solar system. While the specific visions of canal-building Martians proved to be fantasies, the underlying questions they addressed remain as relevant today as they were a century ago. The possibility of life on Mars, whether past or present, simple or complex, continues to drive scientific exploration and capture human imagination. The tools have become more sophisticated, but the fundamental quest remains the same: to answer the profound question of whether Earth is unique in harboring life. These early dreams of Martian life, however scientifically naive they may seem today, served an important purpose in preparing humanity for the possibility that life exists beyond Earth. They encouraged the development of the technologies and methodologies that would eventually allow us to explore Mars directly, and they maintained public interest and support for planetary exploration during the early space age. As we prepare to explore the actual scientific search for life on Mars, we carry with us the legacy of these early dreamers and theorists who dared to imagine that the red planet might be home to fellow travelers in the cosmic journey. Their vision, refined by scientific rigor and technological capability, continues to inspire our modern quest to discover whether life exists beyond our terrestrial home. Our peaceful journey now takes us to the dawn of the space age, when humanity first gained the technological capability to reach across the vast gulf of space and touch the surface of Mars with robotic ambassadors. The story of NASA's exploration of Mars represents one of the most remarkable chapters in human scientific achievement, transforming our red neighbor from a distant point of light into a world we know in intimate detail. The journey began in the early 1960s, during the height of the Cold War space race, when both the United States and Soviet Union launched ambitious programs to explore the planets. The first attempts to reach Mars were fraught with failure. Rockets exploded on launch pads, spacecraft lost contact during the journey, and missions that did reach Mars often failed to function properly. These early setbacks earned Mars a reputation as a spacecraft graveyard and demonstrated the immense challenges of interplanetary exploration. The Soviet Union achieved the first successful Mars flyby with Mars 1 in 1962. Though contact was lost before the spacecraft reached its target, NASA's Merinevo, launched in 1964, became the first mission to successfully fly by Mars and return scientific data. The 21 grainy black and white photographs it transmitted back to Earth showed a cratered, moon-like surface that seemed to dash hopes for a life-bearing world. These first close-up images revealed a Mars that appeared dead and sterile, lacking the canals and vegetation that some had hoped to find. Mariner 6 and 7, launched in 1969, provided additional flyby observations that reinforced the initial impression of Mars as a geologically dead world. However, these missions suffered from the limitation of flyby geometry. They could only photograph small portions of the planet during their brief encounters. The Mars they revealed was incomplete and somewhat misleading, focusing on the heavily cratered southern hemisphere, while missing the more geologically diverse northern regions. The breakthrough came with Mariner 9, which became the first spacecraft to orbit Mars in 1971. Arriving during a planet-wide dust storm, the orbiter initially saw only a featureless, dust-shrouded world. But as the storm cleared over the following months, Mariner 9 revealed a Mars of breathtaking geological diversity and complexity. The spacecraft discovered the massive Vales Marineris Canyon system, the towering Olympus Mons volcano, and most importantly, ancient river valleys and flood channels that provided the first concrete evidence that liquid water had once flowed on the Martian surface. These discoveries transformed scientific understanding of Mars from a sterile, moon-like world to a planet with a complex geological history involving volcanism, tectonics, and most significantly, flowing water. The presence of ancient water features suggested that early Mars might have had a warmer, denser atmosphere capable of supporting liquid water on the surface conditions that might have been suitable for life. The Viking program, launched in 1975, represented NASA's most ambitious attempt to search for life on Mars directly. Consisting of 2 orbiters and 2 landers, Viking was specifically designed to detect signs of microbial life in Martian soil. The Viking landers carried sophisticated biological experiments that could detect metabolic activity, organic compounds, and other potential biosignatures in soil samples collected by robotic arms. The Viking landers touched down successfully on the Martian surface in 1976, becoming the first American spacecraft to operate on another planet. The images they transmitted showed a rocky, desert-like landscape under a butterscotch-colored sky. The biological experiments produced tantalizing but ambiguous results. Some tests showed activity that could indicate life, but the failure to detect organic compounds in the soil suggested that the reactions were probably chemical rather than biological in nature. While Viking did not definitively detect life, the mission provided an unprecedented wealth of information about Mars. The orbiters mapped the planet in detail, revealing the full extent of ancient flood channels and providing evidence for a complex hydrological history. The landers operated far longer than planned, with Viking 1 continuing to transmit data until 1982, providing years of weather observations and surface analyses. After Viking, budget constraints and shifting priorities led to a nearly 2-decade gap in U.S. Mars exploration. The Soviet Union continued attempting Mars missions with mixed success, but technical difficulties and the eventual collapse of the Soviet Union ended their Mars program. Mars exploration entered a quiet period during the 1980s and early 1990s, though scientists continued analyzing Viking data and developing new theories about Martian geology and potential for life. NASA returned to Mars in 1997 with the Mars Pathfinder mission, which demonstrated new, cost-effective technologies for planetary exploration. The mission included a stationary lander and a small rover named Sojourner, the first successful rover to operate on Mars. Pathfinder S airbag landing system and Sojourner S autonomous navigation capabilities pioneered techniques that would be used in future Mars missions. The success of Pathfinder ushered in a new era of Mars exploration characterized by smaller, more frequent missions. The Mars Global Surveyor Orbiter, launched in 1996, began a systematic mapping campaign that revealed Mars in unprecedented detail. Its observations included the first evidence for recent water activity on Mars, in the form of gully formations that appear to have been carved by liquid water. In geologically recent times, the Mars Odyssey orbiter, launched in 2001, made one of the most significant discoveries in Mars exploration. when its instruments detected vast quantities of subsurface water ice, particularly in the polar regions. This discovery confirmed that Mars contains substantial water reserves that could potentially support life or future human exploration missions. The twin Mars exploration rovers, Spirit and Opportunity, launched in 2003, were designed to search for evidence of past water activity on Mars. Both rovers far exceeded their planned 90-day missions, with Opportunity operating for nearly 15 years until 2018. These rovers provided definitive evidence that liquid water had existed on Mars for extended periods in the past, discovering mineral formations that could only have formed in the presence of standing water. The Mars Reconnaissance Orbiter, launched in 2005, continues to provide high-resolution images and detailed mineralogical data about Mars. Its observations have revealed the planet's hydrological history in remarkable detail, showing evidence for ancient lakes, rivers, and even possible oceans. The orbiter also discovered recurring slope linear seasonal dark streaks that might indicate present-day liquid water activity. Each mission has built upon the discoveries of its predecessors, gradually revealing Mars as a world with a complex history that includes periods when conditions might have been suitable for life. The cumulative knowledge gained from decades of exploration has transformed our understanding of Mars from a simple, sterile world to a planet with a rich geological and potentially biological history that continues to unfold today. As we drift deeper into the mysteries of Mars, we encounter the most crucial element in the search for life water, that precious liquid that makes life possible on Earth and whose presence or absence on Mars holds the key to understanding whether our red neighbor could ever have supported living organisms. The story of water on Mars is a tale of abundance and loss, of ancient rivers and hidden reservoirs, of a planet that may have once been as blue as our own Earth. Water serves as the universal solvent for life as we understand it, facilitating the chemical reactions that sustain living processes, and providing the medium in which the complex molecules of life can interact and evolve. On Earth, wherever liquid water exists, from the deepest ocean trenches to the most arid deserts, life finds a way to flourish. This fundamental connection between water and life makes the search for past or present water on Mars central to astrobiology and our hopes of finding life beyond Earth. The earliest evidence for water on Mars came from orbital observations of ancient valley networks that carved through the planet's southern highlands. These branching channel systems bear striking resemblances to river valleys on Earth, suggesting that liquid water once flowed across the Martian surface in quantities sufficient to erode substantial geological features. The preservation of these ancient waterways in Mars' thin atmosphere speaks to their great age and the dramatically different conditions that must have existed billions of years ago. Mariner 9's revolutionary observations in the early 1970s revealed not only small valley networks, but also enormous outflow channels that dwarf any terrestrial river system. These massive flood channels, such as the Cascade Vales and Cris Planitia outflows, appear to have been carved by catastrophic floods involving more water than exists in all of Earth's Great Lakes combined. The scale and violence of these ancient deluges suggest that Mars once held vast reservoirs of water that were episodically released in planet-shaping flood events. The mineral evidence for ancient water activity on Mars provides perhaps the most compelling proof of the planet's watery past. Mars rovers and orbiters have identified numerous clay minerals, sulfates, and other hydrated minerals that can only form in the presence of liquid water. These mineral signatures are found in rock formations that date back over 3 billion years, indicating that the early history of Mars was intimately connected with aqueous processes. Particularly intriguing are the discovery of hematite formations that appear to have formed in ancient hot springs or hydrothermal systems. On Earth, such environments are among the most promising locations for the origin of life, hosting extremophile organisms that thrive in conditions of high temperature and unique chemistry. The presence of similar formations on Mars suggests that the planet may have harbored environments conducive to the emergence and evolution of life. The Mars exploration rovers provided ground truth for orbital observations, by directly analyzing rocks and soils that showed clear evidence of past water activity. Opportunities exploration of Meridiani Planum revealed sedimentary rocks containing mineral formations characteristic of evaporated saltwater, suggesting the existence of ancient shallow seas or lakes. Spirit S investigations in Gussav Crater uncovered evidence for hot spring deposits and other indicators of past hydrothermal activity. Beyond the geological evidence for ancient surface water, Mars harbors substantial quantities of water ice both at its poles and buried beneath its surface. The Mars Odyssey Orbiter's neutron spectrometer revealed that much of the Martian subsurface, particularly at high latitudes, contains significant amounts of water ice mixed with soil and rock. This buried ice represents a vast reservoir of water that could potentially be accessed by future missions or even by hypothetical subsurface life forms. The polar ice caps of Mars contain enormous quantities of both water ice and frozen carbon dioxide. The northern polar cap, in particular, consists primarily of water ice with a volume comparable to Earth's Greenland ice sheet. These polar deposits undergo seasonal cycles of sublimation and deposition, creating dynamic systems that exchange water and carbon dioxide between the atmosphere and surface ice reservoirs. Recent discoveries have provided tantalizing hints that liquid water might still exist on Mars. Under certain conditions, the recurring slope linear observed by the Mars Reconnaissance Orbiter appear as dark streaks that develop seasonally on steep slopes, particularly during warmer periods. While the exact nature of these features remains debated, they may represent brief flows of briny water that can remain liquid at Martian temperatures. Due to their high salt content, the detection of subsurface liquid water reservoirs has been one of the most exciting recent developments in Mars exploration. Radar observations from orbiting spacecraft have identified what appears to be a large lake of liquid water beneath the southern polar ice cap. This sublatial lake, similar to those found beneath Antarctica on Earth, could represent a stable, long-term habitat for microbial life if it exists on Mars. The story of water on Mars is also a story of atmospheric loss and planetary climate change. Early Mars appears to have had a much thicker atmosphere, capable of supporting liquid water at the surface, but the gradual loss of this atmosphere, primarily due to the planet's weak magnetic field, allowing solar wind to strip away gases, led to the cold, dry conditions we observe today. Climate models suggest that early Mars experienced periods of warmth and wetness alternating with cold, dry intervals. These climatic oscillations may have been driven by changes in the planet's orbital characteristics, volcanic outgassing, or asteroid impacts that temporarily thicken the atmosphere. During warm, wet periods, Mars may have supported standing bodies of water and potentially habitable conditions. The search for present-day liquid water on Mars continues with each new mission. The detection of seasonal methane emissions in the Martian atmosphere has been linked to possible subsurface water activity, as methane can be produced by geological processes involving liquid water, or potentially by biological processes. Understanding the source of Martian methane remains one of the key objectives of current and future Mars exploration missions. Hydrated minerals continue to be discovered across Mars, indicating that water-rock interactions were widespread and occurred over extended periods of Martian history. These discoveries paint a picture of a planet where water played a central role in geological and potentially biological processes for billions of years, creating environments that might have supported the emergence and evolution of life. The implications of Mars water history extend far beyond geology to touch the fundamental questions of astrobiology. If Mars once harbored abundant liquid water for extended periods, and if that water supported the chemical processes that could lead to life, then our neighboring planet may have been or may still be a haven for biological activity. The careful study of Martian water in all its forms and throughout its history represents our best hope for answering the profound question of whether life exists beyond Earth. Let's float gently toward the most delicate and sophisticated aspect of astrobiology, the search for biosignatures, those subtle chemical and physical traces that could reveal the presence of past or present life. On Mars, this search requires the careful application of scientific detective work. seeking clues so faint they might easily be overlooked, yet so significant they could transform our understanding of life in the universe. A biosignature represents any measurement or observation that provides convincing evidence of life, whether past or present. On Mars, where no obvious signs of life are visible from orbit or from the surface, scientists must look for more subtle indicators, patterns in atmospheric gases, unusual mineral formations, specific organic compounds, or microscopic structures that could only have been created by living processes. The challenge of identifying biosignatures lies in distinguishing between evidence of life and similar patterns that might be produced by non-biological processes. Many chemical reactions can produce organic compounds, create mineral formations, or alter atmospheric compositions in ways that might initially appear biological, but actually result from purely geological or chemical processes. This ambiguity requires multiple lines of evidence and careful analysis to build a convincing case. For biological activity, atmospheric biosignatures represent one of the most promising avenues for detecting life on Mars. On Earth, the presence of oxygen and methane in the same atmosphere creates a chemical disequilibrium that can only be maintained by biological processes. Oxygen is highly reactive and would quickly disappear from the atmosphere unless continuously replenished by photosynthetic organisms. Similar atmospheric disequilibria on Mars could indicate biological activity. The detection of methane in the Martian atmosphere has become one of the most intriguing potential biosignatures under current investigation. Methane has been observed by both orbital missions and surface rovers, appearing to vary seasonally and spatially across the planet. On Earth, the vast majority of atmospheric methane is produced by biological processes, though geological processes involving water and rock interactions can also generate this gas. Under certain conditions, the seasonal variation of Martian methane adds to its mystery and potential significance. Observations suggest that methane concentrations increase during warmer periods and decrease during colder times, possibly indicating biological activity that responds to seasonal temperature changes. Alternatively, these variations could result from seasonal changes in geological processes or the stability of subsurface methane reservoirs. Organic compound biosignatures involve the detection of complex, carbon-based molecules that could indicate biological activity. While organic compounds can form through non-biological processes, certain patterns of organic molecules, particularly complex mixtures, or compounds with specific handedness or isotopic ratios, might indicate biological origins. The Curiosity rover has detected several organic compounds in Martian rocks, though their origins remain uncertain. Mineral biosignatures focus on identifying rock formations and mineral assemblages that could only have formed through biological processes. On Earth, certain minerals form exclusively through biological activity, such as those created by biomineralization processes, where organisms control the formation of mineral structures. Similar mineral signatures on Mars could provide strong evidence for past life. Particularly intriguing are potential biosignatures related to iron minerals, which can be formed both biologically and geologically. Some iron-bearing minerals show distinctive patterns when formed by microorganisms that differ from those created through purely chemical processes. The widespread presence of iron minerals on Mars makes this a promising area for biosignature research. Isotopic biosignatures examine the ratios of different isotopes of elements like carbon, sulfur, and nitrogen in Martian samples. Biological processes often preferentially use lighter isotopes, creating distinctive isotopic signatures that can persist in rocks and minerals long after the organisms that created them have disappeared. These isotopic patterns provide a way to detect ancient life even when no other traces remain. The search for morphological biosignatures involves looking for microscopic structures that could represent fossilized microorganisms or their traces. This search requires extremely high-resolution imaging and careful analysis to distinguish between biological structures and similar-looking formations created by non-biological processes. The controversial claims about microfossils in Martian meteorites highlight both the potential and the challenges of this approach. Textural biosignatures focus on larger-scale patterns and structures that might indicate biological activity, such as stromatolites-layered rock structures created by ancient microbial mats on Earth. While no definitive stromatolites have been identified on Mars, some rock formations observed by rovers show layered patterns that could potentially result from biological processes, though geological explanations are equally plausible. The preservation of biosignatures on Mars faces unique challenges. Due to the planet's harsh surface conditions, the thin atmosphere provides little protection from ultraviolet radiation and cosmic rays, which can destroy organic compounds over time. Additionally, the oxidizing chemistry of Martian soil can break down organic molecules, making their detection more difficult. These factors mean that the best preserved biosignatures are likely to be found in subsurface environments or in rocks that have been recently exposed. Current Mars missions are specifically designed to search for biosignatures, using increasingly sophisticated instruments. The Perseverance rover carries a suite of instruments capable of detecting organic compounds, analyzing mineral compositions, and even collecting samples for eventual return to Earth, where they can be studied with laboratory precision impossible to achieve on Mars itself. The sample return mission, planned for the late 2020s or early 2030s, represents the next major step in biosignature research. By bringing carefully selected Martian samples back to Earth, scientists will be able to apply the full range of analytical techniques available in terrestrial laboratories, potentially providing definitive answers about the presence or absence of life on Mars. The interpretation of potential biosignatures requires extraordinary care and scientific rigor. The claim of life beyond Earth demands extraordinary evidence, and any putative biosignatures must withstand intense scrutiny and evaluation by the global scientific community. This process ensures that discoveries of life, when they come, will be based on solid, reproducible evidence rather than premature speculation. The search for biosignatures also involves understanding the limits of life itself. What conditions are required for organisms to survive and thrive, and what traces they might leave behind? This research draws heavily on studies of extremophile organisms on Earth that live in conditions similar to those found on Mars, providing insights into what kinds of biosignatures might be produced by life in such harsh environments. As our instruments become more sensitive and our understanding of life's possibilities expands, the search for biosignatures on Mars continues to evolve. Each new discovery, whether of organic compounds, unusual mineral formations, or atmospheric anomalies, adds to our understanding of Mars as a potentially habitable world and brings us closer to answering the fundamental question of whether life exists beyond Earth. Our peaceful journey now takes us to Earth's most extreme environments, where we discover remarkable organisms called extremophiles life forms that thrive in conditions once thought to be absolutely lethal to living things. These extraordinary creatures expand our understanding of life's possibilities and provide crucial insights into how organisms might survive and flourish in the harsh conditions that characterize Mars and other worlds beyond our own. Extremophiles represent some of the most ancient forms of life on Earth, often belonging to groups of microorganisms that have remained essentially unchanged. For billions of years, their ability to survive in conditions of extreme temperature, pressure, acidity, alkalinity, radiation, and chemical toxicity demonstrates that life is far more resilient and adaptable than early biologists imagined. These organisms have rewritten our understanding of life's limits and expanded the range of environments where we might expect to find living organisms. Thermophiles represent perhaps the most well-known category of extremophiles, thriving in temperatures that would instantly kill most familiar forms of life. These heat-loving organisms are found in hot springs, deep-sea hydrothermal vents, and geothermal areas where temperatures can exceed the boiling point of water. Some hyperthermophiles can survive and reproduce at temperatures above 250 F, using specialized proteins and cellular structures that remain stable under conditions that would denature ordinary biological molecules. At the other extreme, psychrophiles flourish in permanently frozen environments such as Antarctic ice, permafrost, and the deep ocean where temperatures hover near or below freezing. These cold-loving organisms have developed antifreeze proteins, modified cellular membranes, and specialized enzymes that function efficiently at low temperatures. Their existence suggests that life could potentially survive in the permanently frozen subsurface of Mars, or other cold worlds in our solar system. Acidophiles thrive in environments with pH levels so low they would dissolve metal, such as acid mine drainage, sulfuric hot springs, and volcanic areas. These acid-loving organisms maintain their internal pH within livable ranges, while extracting energy from chemical processes that would be toxic to most life forms. Their adaptations include specialized cell walls, unique transport systems, and novel metabolic pathways that can function in highly corrosive environments. Alkalophiles represent the opposite extreme, flourishing in highly basic environments with pH levels exceeding 9 or 10, such as soda lakes and alkaline soils. These organisms face different but equally challenging chemical conditions, requiring adaptations to maintain cellular function in environments where ordinary proteins would be destroyed by the high alkalinity. Their existence expands the range of chemical environments where life might be found on other worlds. Halophiles, or salt-loving organisms, thrive in environments with salt concentrations that would dehydrate and kill ordinary life forms. Found in salt lakes, salt mines, and other high porcelain environments, these organisms have developed unique mechanisms for maintaining water balance and cellular function, despite external salt concentrations that can be several times higher than seawater. This adaptation is particularly relevant to Mars, where any present-day liquid water would likely be extremely salty. Radiorestant organisms can survive levels of ionizing radiation that would be lethal to humans and most other life forms. The bacterium Deinococcus radiodurans, for example, can survive radiation doses hundreds of times higher than what would kill a human, repairing massive DNA damage through sophisticated cellular mechanisms. This resilience is crucial for understanding how life might survive on Mars, where the thin atmosphere provides little protection from cosmic radiation and solar ultraviolet light. Barophiles flourish under extreme pressure conditions, such as those found in the deepest ocean trenches, where pressures can exceed 1,000 times atmospheric pressure. These pressure-loving organisms have evolved specialized proteins and cellular structures that function optimally under high-pressure conditions. While Mars currently has very low atmospheric pressure, understanding pressure adaptations helps scientists consider life's possibilities in subsurface environments where pressure conditions might be more favorable. Perhaps most remarkably, some extremophiles can survive in multiple extreme conditions simultaneously. Organisms that are simultaneously thermophilic and acidophilic, or halophilic and radiorestant. These polyextremophiles demonstrate that life can adapt to complex combinations of challenging conditions, suggesting that the habitable zone around stars and within planetary systems might be much broader than previously imagined. The metabolic diversity of extremophiles is equally impressive, with many species deriving energy from chemical processes that would be toxic to ordinary organisms. Camellithotrophs obtain energy by oxidizing inorganic compounds such as sulfur, iron, or methane, processes that could potentially operate on Mars where organic nutrients might be scarce. But chemical energy sources could be abundant in certain environments. Anaerobic extremophiles thrive in oxygen-free environments, obtaining energy through fermentation or using alternative electron acceptors such as sulfate, nitrate, or carbon dioxide. Since Mars has virtually no oxygen in its atmosphere, any Martian life would almost certainly need to be anaerobic, making these organisms particularly relevant models for understanding how life might function on the red planet. The study of extremophiles has revealed that many of Earth's most extreme environments are not only habitable but actually teeming with life. Deep-sea hydrothermal vents, once thought to be sterile due to their extreme heat and toxic chemistry, host entire ecosystems based on chemosynthetic bacteria. Acid mine drainage, which creates conditions similar to battery acid, supports thriving communities of acidophilic microorganisms. Subsurface extremophiles have been found, living miles below Earth's surface in rock formations where they derive energy from geological processes and have been isolated from surface conditions for millions of years. These deep subsurface communities suggest that similar life forms could potentially exist in Mars' subsurface, where they would be protected from surface radiation and temperature extremes, while accessing chemical energy sources from rock-water interactions. Cryptolithic organisms live within rocks themselves, occupying tiny pore spaces and fractures where they find protection from harsh surface conditions, while accessing minimal amounts of light or chemical energy. These rock-dwelling organisms have been found in some of Earth's most Mars-like environments, including Antarctica's dry valleys, providing direct analogues for how life might exist on Mars today. The discovery of extremophiles has fundamentally changed astrobiology by demonstrating that life's requirements are far less restrictive than previously believed. Rather than requiring moderate temperatures, neutral pH, and abundant organic nutrients, life can thrive using a wide variety of energy sources in conditions that would have been considered absolutely prohibitive to biological activity just a few decades ago. These remarkable organisms also provide insights into how life might have originated on early Earth, or other worlds under conditions very different from those that support complex life today. Many extremophiles belong to ancient lineages that may preserve characteristics of the earliest life forms, suggesting that life might naturally arise in extreme environments, rather than requiring the moderate conditions previously thought necessary. The study of extremophiles continues to expand our understanding of life's possibilities, while providing concrete examples of how organisms might adapt to Martian conditions. Each new extreme environment where life is discovered expands the potential habitable zone on Mars and other worlds, suggesting that life might find a way to establish itself in environments that seem utterly hostile to biological activity. As we drift deeper into the cosmic connection between worlds, we encounter one of the most remarkable phenomena in planetary science: meteorites that have journeyed across the void of space, from Mars to Earth, carrying within their ancient crystals potential clues about life on our neighboring world. These rare messengers from Mars provide the only samples of Martian material that scientists can study in terrestrial laboratories with the full power of Earth-based analytical techniques. The story of Martian meteorites begins with violent impacts on the red planet's surface. When large asteroids or comets strike Mars with sufficient energy, they can excavate material from the planet's crust and launch it into space at velocities exceeding Mars' escape velocity of 5 kilometers per second. Most of this ejected material falls back to the Martian surface, but a small fraction escapes into interplanetary space, beginning a journey that may last millions of years before eventually intersecting Earth's orbit. The identification of rocks as genuine Martian meteorites requires careful analysis of their chemical and isotopic compositions. The key evidence comes from trapped gases within the meteorites that match the unique composition of the Martian atmosphere as measured by Viking and later missions. The ratios of different isotopes of noble gases like argon, neon, and xenon provide a distinctive fingerprint that definitively identifies these rocks as originating from Mars rather than from asteroids or other planetary bodies. Currently, scientists have identified approximately 277 meteorites as originating from Mars, though they likely represent fragments from far fewer impact events, perhaps as few as 5 to 10 separate ejections from the Martian surface. These meteorites fall into several distinct groups based on their mineralogy and formation ages, providing insights into different periods of Martian geological history and different regions of the planet's surface and subsurface. The Shogotites, named after the Shogoti meteorite that fell in India in 1865, represent the largest group of Martian meteorites. These rocks are relatively young basalts, formed from volcanic activity on Mars within the past 600 million years. Their study has revealed details about Martian volcanism and the chemical evolution of the planet's interior, showing that Mars remained geologically active much more recently than previously suspected. Naklites, named after the Nakla meteorite that fell in Egypt in 1911, are older rocks that crystallized from magma about 1.3 billion years ago. These meteorites contain minerals that show evidence of alteration by liquid water, providing direct proof that water-rock interactions occurred on Mars, and suggesting that liquid water persisted on or near the Martian surface much longer than initially believed. Chassignites, represented primarily by the Chassigny meteorite, are rare specimens that appear to have formed deep within Mars' crust or mantle. These rocks provide insights into the planet's interior composition and the processes that occurred during Mars' early differentiation, when denser materials sank toward the center, while lighter materials rose toward the surface. The most famous and controversial Martian meteorite is ALH8401, a rock discovered in Antarctica in 1984 that formed on Mars over 4 billion years ago during the planet's earliest history. In 1996, a team of scientists led by David McKay announced that this meteorite contained potential evidence for ancient Martian life, including microscopic structures that resembled fossilized bacteria, organic compounds, and mineral formations associated with biological activity on Earth. The claims about ALH8401 sparked intense scientific debate and scrutiny, while the original interpretations of biological signatures in the meteorite have been largely discredited, with most features being explainable through non-biological processes. The controversy highlighted both the potential importance of Martian meteorites for astrobiology and the extraordinary care required to establish convincing evidence for extraterrestrial life. Recent studies of Martian meteorites have revealed organic compounds in several specimens, including complex carbon-bearing molecules that could potentially serve as building blocks for life. While these organic compounds can form through non-biological processes, their presence demonstrates that Mars has the chemical ingredients necessary for life, and that these compounds can survive both the violent ejection from Mars and the journey through space to Earth. The preservation of organic compounds in Martian meteorites also provides insights into how biological signatures might be preserved in Martian rocks. The fact that complex organic molecules can survive the extreme conditions of impact ejection, space travel, and atmospheric entry suggests that similar compounds could be preserved in rocks on the Martian surface, where they might be detected by future missions or sample return efforts. Some Martian meteorites show evidence of shock metamorphism caused by the impact events that ejected them from Mars. These shock features provide information about the energy and conditions of the impacts, helping scientists understand how material can be launched from planetary surfaces and what effects this process might have on any potential biological signatures contained within the rocks. The discovery of water-bearing minerals in several Martian meteorites has provided direct evidence that liquid water interacted with Martian rocks for extended periods. These hydrated minerals formed through low-temperature aqueous processes, suggesting that Mars had environments where liquid water remained stable long enough to alter rock chemistry conditions that might have been suitable for life. Isotopic analysis of Martian meteorites has revealed important information about Mars' atmospheric evolution and climate history. The isotopic ratios of elements like carbon, nitrogen, and sulfur in the meteorites provide clues about how the Martian atmosphere has changed over time, including evidence for significant atmospheric loss that transformed Mars from a warmer, wetter world to the cold, dry planet we observe today. The study of cosmic ray exposure ages in Martian meteorites indicates that these rocks typically spend millions of years traveling through space before reaching Earth. This long transit time means that the meteorites have been exposed to cosmic radiation for extended periods, which could affect the preservation of organic compounds or other potential biosignatures. Though some materials can survive even these harsh conditions, the crystallization ages of Martian meteorites span billions of years of Martian history, from ALH8401's formation over 4 billion years ago to the young Shergottites that crystallized relatively recently in geological terms. This temporal range provides insights into the long-term evolution of Mars and suggests that volcanic activity and crustal formation processes continued on Mars much longer than on smaller planetary bodies. Future sample return missions from Mars will provide carefully selected and documented samples that can be compared with the randomly delivered Martian meteorites. These controlled samples will help scientists better understand the geological context of the meteorites and determine how representative they are of the broader Martian surface and subsurface. The study of Martian meteorites continues to provide unique insights into the red planet's history, composition, and potential for life. As analytical techniques become more sensitive and new meteorites are discovered, these ancient messengers from Mars will continue to inform our understanding of our planetary neighbor and the possibility that it may have harbored life in its distant past or hidden corners of its present. Our peaceful journey now carries us to the most sophisticated and ambitious attempt yet undertaken to search for signs of life on Mars, the Perseverance rover mission, which landed in Jezero crater in February 2021 with the specific mandate to seek evidence of ancient microbial life on the red planet. This remarkable robotic explorer represents the culmination of decades of technological development and scientific planning, carrying instruments capable of detecting biosignatures with unprecedented precision and sensitivity. Perseverance, officially known as the Mars 2020 mission, was designed from the beginning with astrobiology as its primary objective. Unlike previous Mars rovers that focused primarily on geology and climate history, this mission specifically targets the search for signs that microscopic life may have existed on Mars billions of years ago, when conditions on the planet were warmer and wetter than they are today. The selection of Jezero crater as Perseverance's landing site was based on extensive orbital observations that revealed compelling evidence for an ancient lake environment. This 28-mile-wide crater contains a well-preserved river delta, where flowing water once deposited sediments rich in clay minerals, exactly the type of environment where life might have thrived on early Mars and where biosignatures would be most likely to be preserved. The rover's landing on February 18, 2021, marked a triumph of engineering precision, using an innovative sky crane system that gently lowered the nuclear-powered rover to the Martian surface. This landing system allowed Perseverance to touch down within a few hundred meters of its intended target in terrain that would have been too hazardous for previous landing technologies, demonstrating the advancing capabilities of interplanetary exploration. Perseverance carries 7 scientific instruments specifically selected for their ability to search for biosignatures and understand the geological context of any potential discoveries. The PIXL instrument uses X-ray imaging and spectroscopy to identify and map minerals at microscopic scales, while Sherlock employs ultraviolet laser spectroscopy to detect organic compounds and minerals that might indicate past biological activity. The rover's SuperCam instrument represents a remarkable advancement in remote sensing capability, using laser spectroscopy to analyze the composition of rocks and soil from distances up to 20 feet. This instrument can identify organic compounds, analyze mineral compositions, and even detect trace amounts of water in Martian materials, providing crucial information for selecting the most promising samples for detailed study. Perhaps most significantly, Perseverance carries the first ground-penetrating radar ever deployed on Mars, capable of imaging subsurface structures up to 30 feet below the surface. This radar system, called RIMFAX, can detect buried rock layers, water ice deposits, and other subsurface features that might provide clues about Mars' hydrological history and potential subsurface habitats. The MOXIE experiment aboard Perseverance demonstrates technology for producing oxygen from the Martian atmosphere, successfully converting carbon dioxide into breathable oxygen. While not directly related to the search for life, this technology demonstration shows how future human missions might utilize Martian resources, potentially enabling the human exploration necessary to fully answer questions about life on Mars. One of Perseverance's most important capabilities is its sample collection and caching system, designed to collect carefully selected rock and soil samples for eventual return to Earth by future missions. The rover can drill into rocks, extract core samples about the size of a piece of chalk, and seal them in ultra-clean containers that preserve their scientific integrity for transport back to Earth. The sample selection strategy focuses on rocks that are most likely to preserve biosignatures, including fine-grained sedimentary rocks that formed in the ancient lake environment, hydrothermal deposits that might have supported chemosynthetic life, and organic-rich materials that could contain direct evidence of biological activity. Each sample is carefully documented with high-resolution images and spectroscopic data to provide geological context. Early discoveries from Perseverance have already revolutionized our understanding of Jezero crater's history. The rover confirmed that the crater indeed hosted a large lake fed by a river system, and it discovered that this aquatic environment persisted for much longer than previously estimated, possibly millions of years, which would have provided ample time for life to emerge and evolve if conditions were suitable. The rover's analysis of sedimentary rocks in the crater has revealed organic compounds in multiple samples, suggesting that carbon-based chemistry was active in the ancient Martian environment. While these organic compounds could have formed through non-biological processes, their abundance and diversity increased the possibility that some might have biological origins, highlighting the importance of returning these samples to Earth for detailed analysis. Perseverance's exploration of the Jezero Delta region has uncovered rock formations that show clear evidence of flowing water and sediment deposition over extended periods. The layered structure of these deposits provides a geological record of environmental changes in the ancient lake system, allowing scientists to understand how conditions varied over time and identify periods when they might have been most conducive to life. The discovery of igneous rocks in Jezero crater was unexpected and scientifically significant, indicating that the crater experienced volcanic activity in addition to its aquatic history. These igneous rocks provide opportunities to study Mars' early crustal formation and might contain different types of organic compounds or mineral biosignatures than sedimentary rocks. The rover's weather monitoring instruments have provided detailed information about current Martian atmospheric conditions, including the detection of dust devils, temperature variations, and atmospheric pressure changes. This information helps scientists understand present-day Mars while providing context for interpreting evidence of ancient climates preserved in rocks and minerals. Perseverance's companion helicopter, Ingenuity, has demonstrated powered flight in the thin Martian atmosphere, opening new possibilities for future Mars exploration. While not designed to search for life directly, Ingenuity has provided aerial perspectives of Jezero crater that help scientists plan the rover's exploration strategy and identify the most promising areas for biosignature investigation. The search for biosignatures requires distinguishing between organic compounds that might have biological origins and those formed through geological processes. Perseverance's instruments can identify different types of organic molecules and analyze their distribution patterns, providing clues about their formation mechanisms. Complex organic molecules in specific geological contexts might indicate biological activity, while simpler compounds distributed randomly could suggest non-biological formation. The rover's investigation of mineral formations has focused on identifying those that might preserve biosignatures over geological timescales. Certain clay minerals and sulfates can protect organic compounds from radiation and oxidation, potentially preserving evidence of ancient life for billions of years. The presence of these protective minerals increases the likelihood that any biosignatures present in Jezero rocks will have survived to the present day. Future analysis of Perseverance's samples on Earth will employ techniques impossible to implement on Mars, including high-resolution microscopy, mass spectrometry, and isotopic analysis with precision far exceeding what can be achieved with rover-based instruments. These Earth-based analyses will provide definitive answers about whether the samples contain evidence of ancient Martian life. The Perseverance mission represents a crucial step in the decades-long effort to answer the question of life on Mars. By collecting samples from one of the most promising locations on the planet and preparing them for return to Earth, this mission brings us closer than ever before to obtaining definitive evidence about whether life once existed on our planetary neighbor. The careful, systematic approach of this mission ensures that any discoveries will be based on rigorous scientific evidence capable of withstanding the scrutiny that such extraordinary claims would naturally receive. As our journey continues deeper into the mysteries of Mars, we drift beneath the russet surface into realms of quiet wonder. The gentle transition from the harsh, wind-swept plains above to the protected sanctuaries below feels like descending into a cathedral of stone where silence holds ancient secrets and darkness cradles possibility. In the hidden depths of this ancient world, secret chambers wait in stillness, carved by waters that once whispered through stone corridors millions of years ago. These subterranean galleries stretch endlessly through the planet's quiet heart, their walls bearing the soft signatures of flowing water, ripple marks frozen in time, mineral deposits that speak of gentle chemistry, and smooth channels where ancient streams once meandered through the darkness. Gently, we discover that Mars holds its most precious secrets, not in the harsh light of its surface, but in the soft darkness below. Here, protected from the relentless cosmic radiation that bathes the planet's exterior, temperatures fluctuate more gently, creating microclimates that breathe with stability. The underground realm exists in a state of perpetual twilight, neither fully warm nor completely frozen, but suspended in that delicate balance where life finds its quiet foothold. These underground sanctuaries breathe with possibility, vast networks of caves and tunnels, where life might have found refuge when the surface grew cold and still. We sense the profound interconnectedness of these hidden highways, branching and converging like the root systems of some vast, buried tree. Each tunnel tells its own whispered story of formation, some carved by ancient lava flows that cooled into hollow tubes, others dissolved slowly by groundwater seeping through fractured rock. Like whispers in the night, scientists speak of lava tubes stretching for kilometers beneath Martian soil, their walls protecting whatever dwells within from the gentle but relentless cosmic radiation above. These natural shelters formed billions of years ago, when molten rock flowed across the planet's surface, leaving behind empty channels that now serve as potential havens. The walls of these tubes, smooth and dark, maintain temperatures that hover just above freezing, warm enough for liquid water to exist, gentle enough for delicate biological processes to unfold. In the quiet space of these hidden worlds, we observe how the planet's own geological processes create sanctuaries for life. Hydrothermal systems deep below the surface generate warmth that rises slowly through the rock, creating pockets of relative comfort in an otherwise harsh environment. These thermal oases dot the underground landscape like scattered islands of possibility, each one a potential nursery for Martian life. We sense the profound stillness of underground lakes, their dark waters holding memories of warmer times. These hidden seas rest in chambers carved from solid rock, their surfaces undisturbed by wind or weather. The water moves with the patience of geological time, circulating slowly through interconnected caverns, carrying dissolved minerals and perhaps the building blocks of life itself. Here, in these peaceful depths, microorganisms might drift in eternal calm, sustained by the planet's own gentle warmth rising from its core. We imagine communities of bacteria clustering around warm springs, their metabolisms adapted to the chemical signatures of Mars itself. These theoretical organisms would live not off sunlight, but off the planet's own chemical energy, iron oxidation, sulfur reduction, and the countless other gentle reactions that occur when water meets rock in the patient darkness. The underground water systems of Mars represent a vast, three-dimensional ocean hidden beneath our feet. Unlike the surface, where water exists only as ice or vapor, these subterranean realms maintain liquid water in stable, protected environments. The water moves through interconnected pore spaces in the rock, through fractures and fissures, creating a circulatory system that spans continents. As we drift deeper into understanding these hidden worlds, we discover how they connect across vast distances. A drop of water entering the ground near the polar ice caps might eventually emerge in an underground spring thousands of kilometers away, having traveled for centuries through the planet's patient plumbing system. This underground ocean represents one of the solar system's largest bodies of liquid water, rivaling even some of the moons of Jupiter and Saturn in its potential for harboring life. The chemistry of these underground waters tells stories of their own. As water seeps through Martian rock, it dissolves minerals and carries them in solution, creating a rich broth of nutrients that could sustain life. Iron, sulfur, carbon, nitrogen, all the elements essential for biological processes flow through these hidden streams, waiting to be incorporated into living systems. In the deepest chambers, where the planet's internal heat creates warm pockets of stability, we sense environments that might closely resemble Earth's own deep biosphere. Here, miles below the surface, life exists independent of the sun, driving energy from chemical reactions and the planet's own internal warmth. If such communities exist on Mars, they would represent a completely independent genesis of life, a second experiment in biology occurring in the quiet depths of our neighboring world. The search for these underground sanctuaries requires patient listening. Scientists use seismic instruments to sense the subtle vibrations that reveal hidden cavities in the rock. They measure variations in the planet's magnetic field that hint at underground water flows. They watch for subtle changes in surface temperature that betray the presence of warm springs hidden below. Each piece of evidence whispers of a Mars far more complex and alive than the barren surface suggests. The planet breathes through hidden pores in its skin, circulates life-giving fluids through underground arteries, and maintains warm hearths in its deepest chambers. This hidden Mars exists in parallel to the visible one, a secret world of possibility that may harbor the most profound discovery in human history. Now we float toward understanding Mars' lost breath, the atmosphere, that once embraced this world in warmth and possibility. In the quiet space of deep time, we observe how this planet's voice grew softer, its protective blanket slowly drifting away into the cosmic silence, like morning mist dissolving into gentle rays of dawn. The ancient atmosphere of Mars tells a story of gradual transformation, written in layers of rock and ice that preserve the whispered memories of a warmer, wetter world. For billion years ago, when Earth was still young and life was just beginning to stir in our own primordial oceans, Mars breathed deeply with an atmosphere thick enough to support liquid water. Across its entire surface, gently, we discover that ancient Mars once breathed deeply. Its atmosphere thick enough to cradle liquid water on its surface. The planet wore clouds like soft garments, and weather systems drifted across continents in patterns that created seasons and storms. Rain fell gently on vast plains and ancient highlands, pooling in crater lakes and flowing down channel systems that carved the landscape with patient persistence. This ancient atmosphere consisted primarily of carbon dioxide, but unlike today's thin shell, it was dense enough to create a significant greenhouse effect. Water vapor mixed with the carbon dioxide, creating a feedback system that trapped heat and maintained temperatures warm enough for liquid water to persist. The atmospheric pressure was sufficient to prevent water from immediately boiling away, allowing rivers and lakes to exist in stable equilibrium with their environment. Rivers meandered peacefully across landscapes, and gentle rains whispered against rocks that still bear their soft impressions. We can read these ancient weather patterns in the geological record, the rounded pebbles that speak of stream transport, the sedimentary layers that preserve the rhythms of ancient floods and droughts, and the mineral signatures that form only in the presence of liquid water and protective atmosphere. The deltas and alluvial fans scattered across Mars' surface tell stories of rivers that flowed for millions of years, carrying sediments from highland sources to lowland basins. These features required not just brief episodes of warmth, but sustained climatic conditions that could maintain flowing water across geological timescales. The planet's ancient hydrological cycle operated much like Earth's, with evaporation, cloud formation, precipitation, and surface runoff creating a dynamic system of water movement. Like whispers in the night, the solar wind gradually carried away Mars' atmospheric embrace. This process unfolded over hundreds of millions of years, as charged particles streaming from the sun slowly stripped away the planet's protective gaseous envelope. Unlike Earth, Mars lacked a strong global magnetic field to deflect these particles, leaving its atmosphere vulnerable to this gentle but relentless erosion. The loss occurred particle by particle, molecule by molecule, as solar radiation provided enough energy to accelerate atmospheric gases beyond Mars' escape velocity. The lighter elements departed first, hydrogen escaping most readily. followed by other gases in order of their molecular weight. This selective loss changed the atmospheric composition over time, concentrating heavier gases while depleting the lighter ones. Without the protective touch of a strong magnetic field, the planet's breath grew thinner, more fragile, until only the faintest sigh remained. The magnetic field that once shielded Mars weakened and disappeared as the planet's core cooled, and its internal dynamo shut down. This left the atmosphere completely exposed to solar wind erosion, accelerating the pace of atmospheric loss. We watch in our mind's eye as this transformation unfolded over eons, not with violence, but with the slow, inevitable grace of cosmic change. The planet did not die suddenly, it simply drifted into a deeper, quieter state of being. As the atmosphere thinned, surface pressure dropped below the threshold needed to maintain liquid water. Rivers gradually ceased flowing, lakes evaporated or froze, and the planet's hydrological cycle slowed to a whisper. The climate change that transformed Mars offers profound insights into planetary evolution and the delicate balance that maintains habitable conditions. The transition from a warm, wet world to the cold, dry planet we observe today demonstrates how multiple factors, atmospheric composition, magnetic field strength, solar radiation, and planetary mass interact to determine a world's climate destiny. Evidence for this ancient climate comes from multiple sources scattered across the planet's surface. Valley networks carved by flowing water preserve the drainage patterns of ancient river systems. Crater lakes show evidence of long-term water accumulation and evaporation cycles. Hydrated minerals formed in the presence of liquid water tell chemical stories of ancient weathering processes that required stable atmospheric conditions. The isotopic composition of gases trapped in meteorites from Mars provides direct evidence for atmospheric evolution. The ratios of different isotopes of noble gases preserve signatures of atmospheric loss processes, allowing scientists to reconstruct the history of Mars' atmospheric decline with remarkable precision. These cosmic messengers carry within them the chemical fingerprints of a world in transition. As we drift through understanding of this atmospheric transformation, we sense how it connects to the planet's potential for life. The early, thicker atmosphere created a greenhouse effect that maintained temperatures suitable for liquid water and possibly biological processes. Even as the atmosphere thinned, protected environments like underground caverns and deep crater lakes might have provided refugia where life could persist. The timing of atmospheric loss also suggests that Mars maintained potentially habitable conditions. For hundreds of millions of years, long enough for life to emerge and establish itself. If the right chemical ingredients were present, the gradual nature of climate change would have provided time for any existing life to adapt or retreat to more protected environments. Seasonal variations in Mars' current thin atmosphere provide glimpses of the dynamic processes that once operated on a much larger scale. The polar ice caps still grow and shrink with the seasons, causing measurable changes in atmospheric pressure as carbon dioxide condenses and sublimes. These cycles represent the faint echo of the robust weather systems that once circulated around the planet. Understanding Mars' atmospheric history also informs our knowledge of climate change on Earth and other worlds. The processes that stripped away Mars' atmosphere operate throughout the solar system, affecting every planet and moon. By studying how Mars lost its atmospheric protection, we gain insights into the conditions necessary to maintain habitable environments. Over geological time, the story of Mars' lost atmosphere reminds us of the preciousness of planetary environments and the complex interplay of forces that determine whether a world remains habitable. It speaks to the delicate balance that allows life to flourish and the cosmic processes that can slowly transform entire worlds from garden paradises to frozen deserts. As our journey continues into the gentle realm of astrobiology, we drift among the peaceful disciplines that unite to seek life's hidden presence. Throughout the cosmos, this quiet science weaves together biology, geology, chemistry, and astronomy like soft threads in a cosmic tapestry, creating a new way of understanding life's place in the universe. Astrobiology emerges from humanity's ancient wonder about our place in the cosmos, transformed by modern scientific methods into a rigorous search for life beyond Earth. This interdisciplinary field draws upon the collective wisdom of multiple sciences, each contributing its own perspective to the greater understanding of life's possibilities and requirements. In the quiet space of laboratory and telescope, researchers listen for life's gentle signatures, the subtle chemical whispers that speak of metabolism, growth, and the quiet persistence of living systems. They develop increasingly sensitive instruments, capable of detecting the faintest traces of biological activity, from the spectral signatures of organic molecules to the isotopic ratios that betray metabolic processes. The search for biosignatures requires extraordinary patience and precision. Scientists must distinguish between chemical patterns produced by living processes and those created by purely geological or atmospheric phenomena. This challenge drives the development of new analytical techniques and theoretical frameworks for understanding how life interacts with its environment. On a molecular level, they watch for patterns that breathe with the rhythm of life, even in the most distant and still environments. Seasonal variations in atmospheric composition, diurnal cycles in chemical concentrations, and spatial distributions of organic compounds all potentially carry the subtle fingerprints of biological processes. Each potential signal must be carefully evaluated against alternative explanations, requiring deep understanding of both living and non-living systems. Gently, we discover how this science teaches us to recognize life not just as we know it on Earth, but as it might exist in forms we've never imagined. The study of extremophiles, organisms that thrive in conditions previously thought uninhabitable, has revolutionized our understanding of life's possibilities and expanded the range of environments where we might expect to find living systems. Astrobiologists study organisms that flourish in boiling hot springs, in the crushing depths of ocean trenches, in highly acidic environments, and in regions bombarded by intense radiation. Each extremophile discovered on Earth expands the envelope of conditions under which life might persist, suggesting that the cosmos may harbor forms of biology adapted to environments we can barely imagine. Like explorers of inner worlds, astrobiologists learn to sense the possible in the seemingly impossible. They develop theoretical frameworks for understanding how life might emerge and evolve under different planetary conditions, considering factors like atmospheric composition, temperature ranges, available energy sources, and chemical complexity. The field encompasses the study of life's origins on Earth as a model for understanding how biology might emerge elsewhere. By investigating how non-living matter first organized itself into self-replicating systems, scientists gain insights into the universal principles that govern the transition from chemistry to biology. These studies suggest that life may be an emergent property of complex chemical systems, arising naturally when conditions permit sufficient molecular complexity and energy flow. We observe how they study extremophiles, Earth's quiet survivors that thrive in conditions once thought lifeless. These peaceful organisms show us that life finds ways to flourish in acid pools, frozen depths, and radiation-bathed stones, expanding our understanding of where life might gently persist. Hyperthermophiles live in water hot enough to sterilize medical instruments, driving energy from chemical reactions that occur only at extreme temperatures. Psychrophiles thrive in permanently frozen environments, maintaining liquid cellular contents through specialized proteins and metabolic adaptations. Halophiles flourish in salt concentrations that would dehydrate most organisms, while acidophiles prosper in environments more corrosive than battery acid. These extremophiles demonstrate life's remarkable plasticity and suggest that the habitable zone around stars, traditionally defined by the possibility of liquid water, may be far broader than previously imagined. Life might persist in environments warmed by geological processes rather than stellar radiation, or in chemical environments that drive energy from processes completely independent of photosynthesis. The search for life beyond Earth employs multiple complementary approaches, each designed to detect different aspects of biological activity. Spectroscopic analysis of planetary atmospheres can reveal gases that might be produced by living processes. Microscopic examination of returned samples allows direct observation of potential microbial structures. Chemical analysis can identify organic compounds and assess their complexity and chirality. Remote sensing techniques continue to evolve, allowing increasingly detailed analysis of distant worlds without the need for physical sample. Return. Advanced telescopes can now detect and characterize exoplanetary atmospheres, searching for combinations of gases that might indicate biological processes. The James Webb Space Telescope and future missions will push these capabilities even further, potentially detecting biosignatures in the atmospheres of Earth-like planets around nearby stars. The field also encompasses the study of how life might communicate across interstellar distances. The search for extraterrestrial intelligence SETI represents one branch of astrobiology that focuses on detecting potential technological signatures from advanced civilizations. This work requires sophisticated signal processing techniques and careful consideration of what forms extraterrestrial communication might take. As we drift deeper into understanding astrobiology's methods and goals, we sense how this field transforms our relationship with the cosmos. Rather than seeing space as an empty void punctuated by rare oases of life, astrobiology encourages us to view the universe as potentially teeming with biological activity in forms and locations we are only beginning to imagine. The philosophical implications of astrobiology extend far beyond the purely scientific. The discovery of life elsewhere would fundamentally alter our understanding of biology, evolution, and our place in the cosmic community. It would provide a second data point for understanding life's emergence and development, potentially revealing universal principles that govern biological processes throughout the universe. Astrobiology also grapples with questions of planetary protection, ensuring that human exploration of other worlds does not contaminate potential alien ecosystems or compromise our ability to study them in their pristine state. This ethical dimension of the field reflects our growing awareness of our responsibility as explorers of the cosmic ocean. The interdisciplinary nature of astrobiology fosters collaboration across traditional academic boundaries, bringing together researchers with diverse expertise to tackle questions that no single discipline could address alone. This collaborative approach models a new way of conducting science that may be essential for addressing the complex challenges of the modern world. Research in astrobiology feeds back into our understanding of life on Earth, revealing new insights into evolution, adaptation, and the fundamental requirements for biological processes. By studying how life might function under alien conditions, we gain new perspectives on the mechanisms that sustain terrestrial biology and the factors that have shaped life's development on our own planet. The field continues to evolve rapidly as new discoveries expand our understanding of life's possibilities, and new technologies enable more sophisticated searches for biological activity beyond Earth. Each advance brings us closer to answering one of humanity's most profound questions. Are we alone in the universe, or do we share the cosmos with other forms of life that rose independently under alien skies? Now we float toward contemplating the profound implications that ripple outward from this discovery, like gentle waves across the ocean of human understanding. In the quiet space of reflection, we sense how this knowledge touches every aspect of our existence, our science, our philosophy, our spirituality, and our fundamental conception of what it means to be alive in this vast cosmos. The confirmation of life on Mars represents far more than a scientific milestone. It marks a transformation in humanity's cosmic perspective that will echo through generations. This discovery carries implications that extend from the most technical aspects of biology to the deepest questions of meaning and purpose that have occupied human thought since we first gazed up at the stars in wonder. Gently, we discover that life on Mars whispers to us about our own nature, our origins, and our place in the vast, peaceful cosmos. The existence of a second Genesis life arising independently in our own solar system would demonstrate that biology is not a miraculous accident confined to Earth, but potentially a fundamental feature of the universe itself. This revelation would fundamentally alter our understanding of evolution and the processes that give rise to complex biological systems. If life emerged twice within a single star system, it suggests that the chemical and physical conditions necessary for biology are more common than we previously imagined. The universe begins to appear not as a sterile void with rare oases of life, but as a cosmic ocean where the currents of chemistry and physics naturally flow toward biological complexity. No longer would Earth stand alone as the sole cradle of life. We would find ourselves part of a larger, more interconnected cosmic family. This shift in perspective carries profound psychological and philosophical implications for humanity. The sense of cosmic isolation that has characterized much of human thought gives way to a recognition of kinship that extends beyond our planetary boundaries. The discovery would validate the scientific methodology that led to this moment, demonstrating the power of systematic observation, hypothesis testing, and technological innovation to reveal the deepest truths about our universe. It would represent a triumph of human curiosity and ingenuity, showing that our species possesses the capability to answer questions that have puzzled us for millennia. Like whispers in the night, this knowledge changes how we see ourselves. We are not isolated wanderers in an empty universe, but participants in a grand, quiet symphony of life that may echo throughout countless worlds. This recognition transforms our understanding of human purpose and responsibility, suggesting that we may be part of a larger community of conscious beings distributed throughout the cosmos. The implications for biology and evolution would be staggering. Comparative studies between Martian and Terran life would reveal which aspects of biology represent universal principles and which reflect the particular conditions of Earth's development. We might discover that certain biochemical processes, cellular structures, or genetic mechanisms represent optimal solutions to the challenges of life, independently arrived at by biology on different worlds. Alternatively, we might find that life can take forms so alien to our Earth-based experience that they expand our definition of what it means to be alive. Martian organisms might use different chemical bases for information storage, employ novel metabolic pathways, or organize themselves in ways that challenge our fundamental assumptions about biological systems. We breathe in the possibility that life is not rare and precious only to Earth, but perhaps a gentle, persistent force that emerges wherever conditions allow. This shifts our perspective from one of cosmic loneliness to one of cosmic kinship. The universe transforms from a hostile environment where life struggles against overwhelming odds to a nurturing matrix where biological complexity naturally emerges and flourishes. The statistical implications of finding life on Mars would be profound. If life arose independently onto planets within a single star system, it suggests that biology may be a common feature of planetary evolution throughout the galaxy. The Drake equation, which attempts to estimate the number of communicating civilizations in our galaxy, would require fundamental revision, with potentially dramatic increases in the estimated prevalence of life. This discovery would also transform our approach to space exploration and planetary science. Every world in our solar system would be viewed as a potential harbor for life, deserving careful study and protection. The search for life would become a central organizing principle for space missions, driving technological development and international cooperation on an unprecedented scale. The religious and spiritual implications would be equally profound, requiring theologians and spiritual leaders to grapple with the reality of life beyond Earth. Some religious traditions might find their cosmologies validated by the recognition of life's abundance throughout creation. Others might need to expand their understanding of divinity and sacred purpose to encompass a universe teeming with biological activity. The discovery would likely accelerate the development of a truly cosmic perspective on human existence, what astronauts have described as the overview effect experienced when viewing Earth from space. This shift in consciousness, currently limited to the few hundred humans who have traveled beyond our atmosphere, might become a fundamental aspect of human culture and education. From a practical standpoint, the confirmation of Martian life would drive massive investments in astrobiology, space technology, and related fields. It would likely trigger a new space race, not for national prestige, but for scientific understanding and the expansion of human presence in the solar system. The economic implications alone would be substantial as entire new industries emerge around the study and potential utilization of extraterrestrial biology. The discovery might also accelerate discussions about planetary protection and the ethics of space exploration. If Mars harbors indigenous life, questions about human colonization and terraforming would become far more complex, requiring careful consideration of our responsibilities toward alien ecosystems that took billions of years to evolve. Educational systems worldwide would need to incorporate this new reality into curricula. At all levels, children would grow up knowing that life exists beyond Earth, fundamentally shaping their understanding of biology, astronomy, and their place in the universe. This generation would approach space not as an empty frontier to be conquered, but as a living environment to be respectfully explored and understood. The psychological impact on human society would likely be substantial but ultimately positive, while some might initially experience existential anxiety about humanity's reduced uniqueness. The broader implications suggest a universe rich with possibilities and connections. We would no longer carry the heavy responsibility of being the universe's only conscious observers, but could embrace our role as participants in a cosmic community of life and awareness. The discovery would also provide new perspectives on the challenges facing life on Earth. By studying how Martian life adapted to harsh conditions and dramatic climate change, we might gain insights applicable to Earth's own environmental challenges. Martian organisms might possess biochemical innovations that could inspire new approaches to medicine, agriculture, or environmental remediation. International cooperation would likely increase as nations recognize that the implications of this discovery extend far beyond any single country's interests. The study of Martian life would require the combined resources and expertise of the global scientific community, potentially serving as a catalyst for increased collaboration and peaceful interaction among Earth's nations. As we drift in contemplation of these vast implications, we sense that the discovery of life on Mars would mark not just a scientific achievement, but a fundamental transition in human consciousness, a moment when we cease to think of ourselves as alone and begin to embrace our identity as citizens of a living universe. As our journey continues toward tomorrow's gentle explorations, we drift alongside the peaceful missions that will carry human hearts and minds to the red planet's quiet shores. These future endeavors unfold not with haste, but with the careful, mindful preparation of pilgrims approaching sacred ground, where each step must be taken with reverence for the potential life that may dwell in Mars' hidden sanctuaries. The coming decades will witness an unprecedented expansion of human presence at Mars, driven by the profound implications of discovering life on our neighboring world. These missions represent more than technological achievements. They embody humanity's peaceful commitment to understanding and protecting the cosmic life we have found while expanding our own presence as responsible inhabitants of the solar system. In the quiet space of mission planning, we observe how sample return missions will tenderly gather Martian soil and stone, carrying these precious fragments back to Earth where they can be studied with reverence and care. Each grain of dust becomes a messenger from another world, potentially harboring microscopic ambassadors of an alien biosphere that developed independently from our own. The Mars Sample Return Mission, a collaborative effort between NASA and the European Space Agency, represents one of the most complex robotic endeavors ever attempted. This multi-phase campaign will carefully collect samples from diverse Martian environments, seal them in sterile containers, and transport them across millions of kilometers of space to terrestrial laboratories equipped with instruments too sophisticated to send to Mars. The sample collection process itself requires extraordinary precision and care. Robotic systems will drill into rock formations, scoop soil from various depths, and even attempt to capture atmospheric samples that might contain airborne microorganisms. Each sample will be documented with high-resolution imagery and precise geological context, ensuring that scientists can understand not just what they find, but where and how it formed. These samples will undergo the most intensive biological and chemical analysis in human history, examined by instruments capable of detecting individual molecules and identifying potential biosignatures with unprecedented sensitivity. The laboratories receiving these samples will be designed as biological containment facilities, protecting both the Martian samples from terrestrial contamination and Earth's biosphere from any potential Martian organisms. Gently, we discover the patient preparation for human footsteps on Martian ground. These brave souls will travel not as conquerors, but as gentle ambassadors of Earth, treading softly on soil that may harbor our cosmic neighbors. The journey to Mars requires months of travel through the void between worlds, time that will be spent in careful preparation and contemplation of the momentous task ahead. Human missions to Mars will build upon decades of robotic exploration, utilizing landing sites and infrastructure carefully selected and prepared by automated systems. The first human visitors will arrive at bases already equipped with life support systems, power generation capabilities, and scientific instruments, all delivered and tested by preceding cargo missions. The astronauts selected for these missions will undergo years of training not just in technical skills, but in the philosophical and ethical dimensions of their role as humanity's first ambassadors to a potentially inhabited world. They will carry with them the hopes and dreams of all Earth's inhabitants, representing our species' highest aspiration for peaceful exploration and scientific discovery. Like whispers in the night, these missions speak of humanity's quiet evolution from a single-planet species to citizens of the solar system, moving with respect and wonder through realms previously known only in dreams. This transformation requires not just technological advancement, but a fundamental shift in human consciousness, from seeing space as territory to be claimed to understanding it as sacred ground, to be respectfully explored. The challenges of human Mars exploration extend far beyond the technical difficulties of transportation and life support. The psychological demands of spending months or years on an alien world, potentially in the presence of indigenous life, require careful consideration and preparation. Mission planners are developing protocols for human-alien interaction that prioritize the protection of Martian ecosystems while enabling meaningful scientific study. The presence of humans on Mars will enable research impossible with robotic missions alone. Human flexibility, intuition, and real-time decision-making capabilities will allow for adaptive exploration strategies that can respond to unexpected discoveries. Geologists will be able to examine rock formations with their own eyes, following geological features across Martian landscapes with the trained intuition that only comes from field experience. Biological investigations will benefit enormously from human presence. While robotic systems excel at following programmed procedures, humans can make the kind of spontaneous observations and connections that often lead to breakthrough discoveries. The ability to quickly redirect research efforts based on preliminary findings could accelerate the pace of discovery by orders of magnitude. The infrastructure required to support human presence on Mars will itself represent a technological marvel. Habitation modules must provide not just life support, but psychological comfort for crews spending extended periods in an alien environment. These facilities will be designed to minimize their impact on Martian ecosystems while providing the safety and functionality necessary for successful exploration. Power systems for Mars missions will likely combine multiple technologies. Solar panels for surface operations, nuclear reactors for reliability during dust storms, and fuel cells for mobility systems. The redundancy and reliability required for human safety will drive innovations that benefit space exploration throughout the solar system. In situ resource utilization will allow human missions to become increasingly self-sufficient, extracting water, oxygen, and building materials directly from the Martian environment. This capability will reduce the cost and complexity of supply missions from Earth, while demonstrating humanity's ability to live sustainably on other worlds. The communication challenges of Mars exploration will require new approaches to real-time collaboration between Earth and Mars-based teams. Signal delays ranging from minutes to over 20 minutes mean that Mars explorers must be prepared to make critical decisions independently, while Earth-based support teams provide strategic guidance and analytical support. International cooperation will be essential for human Mars exploration, as no single nation possesses all the resources and expertise required for such ambitious endeavors. The International Space Station has demonstrated the possibility of sustained cooperation in space, and Mars missions will likely expand this collaborative model to include emerging spacefaring nations and private organizations. the protection of potentially existing Martian life will require careful protocols. For human exploration activities, designated protected zones might be established around areas of high biological interest, while human activities are carefully monitored to prevent contamination or disturbance of indigenous ecosystems. This balance between exploration and protection will require ongoing dialogue between scientists, ethicists, and mission planners. Future Mars missions will also serve as stepping stones toward deeper space exploration. The technologies and techniques developed for Mars operations will inform missions to the moons of Jupiter and Saturn, where subsurface oceans might harbor even more complex forms of alien life. Mars will serve as humanity's training ground for becoming a truly spacefaring civilization. The economic model for sustained human presence on Mars remains an active area of development. While initial missions will be government-funded research endeavors, long-term sustainability may require the development of Mars-based industries that can provide economic value to Earth. These might include scientific research, rare mineral extraction, or serving as a way station for deeper space exploration. As we contemplate these future missions, we sense the profound responsibility they carry. Human explorers of Mars will be pioneers not just in the geographical sense, but in establishing the ethical and philosophical frameworks that will guide humanity's expansion into the cosmos. Their careful, respectful approach to exploration will set precedents that shape our species' relationship with other worlds for generations to come. The timeline for these missions stretches across decades, with each phase building upon the successes and lessons of its predecessors. Sample return missions in the 2030s will be followed by human exploration missions in the 2040s, with permanent human presence becoming possible by the 2050s. This gradual, patient approach reflects our commitment to doing this exploration correctly rather than quickly. Now we float toward weaving together all the gentle threads of discovery that have emerged from this cosmic tapestry. In the quiet space of integration, we sense how each element connects to create a greater, more beautiful whole, a unified understanding that transforms isolated facts into a living narrative of cosmic life and human wonder. The discovery of life on Mars does not stand alone as a singular achievement, but represents the convergence of countless human efforts, technological advances, and scientific insights accumulated over generations. Each component of our understanding, from the geological whispers that revealed Mars' watery past, to the sophisticated instruments that detected biological signatures, contributes to a symphony of knowledge that resonates with profound meaning. Gently, we discover how the geological whispers of ancient Mars connect to the biological possibilities hidden in its depths. The valley networks carved by ancient rivers tell us where liquid water once flowed, pointing us toward the underground reservoirs where life might have retreated as the planet's climate changed. The mineral signatures left by hydrothermal systems reveal chemical environments that could have nurtured the first Martian organisms billions of years ago. The atmospheric stories of long ago drift into the present possibilities of underground sanctuaries, where life might still breathe quietly. Mars' lost atmosphere created the conditions that drove life underground, but those same protective depths now offer stability that surface environments cannot provide. The planet's climate history becomes not just a tale of loss, but a guide to understanding where life might persist in the modern era. Like soft melodies harmonizing, the technological achievements that revealed these secrets blend with the philosophical implications that expand our hearts and minds. Each rover that rolled across Martian soil, each orbiter that mapped the planet's surface, and each spectrometer that analyzed chemical compositions represents humanity's patient commitment to understanding. These mechanical ambassadors prepare the way for discoveries that touch the deepest aspects of human consciousness and our place in the universe. The robotic explorers that preceded human missions serve as more than just reconnaissance tools. They embody our species' capacity for extending our senses and presence across impossible distances. Through their electronic eyes and analytical instruments, we have touched an alien world and found it not empty, but potentially alive with possibilities we are only beginning to comprehend. We observe how this knowledge doesn't stand alone, but flows gently into the broader stream of human wisdom. touching our science, our spirituality, our sense of wonder, and our responsibility as stewards of life. Wherever it may be found, the implications ripple outward from astrobiology into philosophy, religion, ethics, and politics, requiring humanity to grapple with questions that transcend any single discipline or cultural perspective. The scientific integration occurs at multiple levels, from the molecular to the planetary. Understanding how Martian life might function at the cellular level informs our broader theories of evolution and biochemistry. Studying how biological processes might influence planetary atmospheric composition connects biology to climate science and atmospheric physics. Each discovery in one field illuminates and is illuminated by insights from related disciplines. The integration of past and future creates a temporal unity that spans billions of years. Ancient geological processes that shaped Mars' early environment connect to current biological possibilities, which in turn inform our plans for future exploration and potential human settlement. Time becomes not a linear progression, but a living continuum where past, present, and future inform and shape each other. The technological integration demonstrates humanity's capacity for collective achievement. The discovery of Martian life required contributions from thousands of scientists, engineers, and support personnel working across decades and continents. No single individual or institution could have accomplished this alone. It represents the power of human collaboration and shared commitment to understanding. International cooperation in Mars exploration exemplifies our species' potential for peaceful collaboration in pursuit of knowledge and understanding. Nations that might compete or conflict in terrestrial affairs find common ground in the shared wonder of cosmic exploration. The search for life beyond Earth becomes a unifying force that transcends political boundaries and cultural differences. The philosophical integration touches the deepest questions of human existence and meaning. The confirmation of life beyond Earth validates our scientific methods, while challenging us to expand our understanding of consciousness, purpose, and cosmic significance. We find ourselves part of a larger community of life, while simultaneously recognizing our unique role as the first species we know of capable of recognizing and protecting life throughout the cosmos. Religious and spiritual traditions find themselves called to integration as well, expanding their cosmologies to encompass a universe where life may be abundant rather than rare. This expansion enriches rather than diminishes spiritual understanding, revealing new depths of meaning in creation and consciousness. The sacred becomes not confined to Earth, but potentially present throughout the cosmos in forms we are only beginning to recognize. The integration of protection and exploration creates new ethical frameworks for space exploration. Our commitment to preserving Martian ecosystems while advancing human knowledge requires balancing competing values and interests. This balance serves as a model for how humanity might approach other worlds and other forms of life we may encounter as our exploration capabilities expand. Economic integration transforms space exploration from a purely scientific endeavor into a sustainable human enterprise. The potential for Mars-based research, resource extraction, and technological development creates new economic models that could support long-term human presence while generating benefits for Earth-based populations. This economic dimension ensures that space exploration can continue and expand beyond the initial phase of discovery. Cultural integration ensures that the implications of discovering Martian life reach beyond scientific communities to influence art, literature, education, and popular culture. The knowledge that we share the cosmos with other forms of life will inspire new forms of creative expression and cultural understanding. Future generations will grow up knowing themselves to be citizens of a living universe, rather than isolated inhabitants of a lonely planet. The integration of risk and responsibility acknowledges that with great discoveries come great obligations. Our power to detect and study life beyond Earth brings with it the responsibility to protect and preserve that life. This ethical dimension of exploration ensures that our expansion into the cosmos serves not just human interests, but the interests of life itself in all its forms. Educational integration transforms how we teach and learn about biology, astronomy, and our place in the universe. The discovery of Martian life will require updating textbooks, curricula, and educational approaches at all levels. Students will need to develop new ways of thinking about life, evolution, and cosmic citizenship that prepare them for a future where interaction with alien life may become routine. As we sense these numerous threads weaving together, we recognize that the discovery of life on Mars marks not an endpoint, but a beginning, the first chapter in humanity's ongoing relationship with the living cosmos. Each element of understanding enhances and is enhanced by the others, creating a coherent vision of our place in a universe that appears increasingly alive with possibility and wonder. As our journey gently draws to its peaceful close, we drift in quiet contemplation of all we have discovered together. In this still moment, we breathe in the profound beauty of what it means to find life beyond our blue home, letting the implications settle into our hearts like morning dew on awakening flowers. The path that brought us to this moment of discovery stretches back through human history. From our earliest ancestors who looked up at the red wandering star and wondered about its nature, to the modern scientists who detected the first whispered signatures of alien biology in Martian soil. Each generation contributed to this achievement, building the knowledge and tools that made such a profound discovery possible. We have journeyed from the surface of Mars deep into its underground sanctuaries, followed the planet's atmospheric breath as it slowly departed into space, and learned to listen for life's subtle signatures with the patient ears of astrobiology. Each step of our exploration has revealed new wonders and deeper mysteries, showing us that the universe is far more complex and beautiful than we ever imagined. Like whispers in the night, this discovery speaks to something deep within us, our ancient longing to know we are not alone, our quiet hope that life finds ways to flourish even in the most remote and challenging places. This fundamental human desire for connection and understanding transcends cultural boundaries and spans generations, uniting us in wonder at the cosmos we inhabit. The longing to find life beyond Earth reflects our deeper need to understand our own nature and purpose. By discovering that life can emerge and persist under conditions very different from those on Earth, we gain new perspective on the processes that created us and the possibilities that lie before us. We are no longer unique accidents in a sterile universe, but participants in a cosmic phenomenon that may be more common and wonderful than we dared hope. Gently, we discover that in finding life on Mars, we have also found something precious about ourselves. We are a species capable of reaching across vast distances, not with violence or conquest, but with curiosity, respect, and wonder. This achievement represents the finest aspects of human nature, our capacity for cooperation, our commitment to understanding, and our ability to look beyond immediate needs to pursue knowledge for its own sake. The technologies that enabled this discovery emerged from human creativity and persistence applied over decades of patient effort. From the first telescopes that revealed Mars as a world rather than a point of light, to the sophisticated rovers that analyzed Martian soil grain by grain, each advancement built upon previous achievements while pushing the boundaries of what seemed possible. The international cooperation that made these missions possible demonstrates humanity's capacity to transcend political divisions in pursuit of shared goals. Scientists from dozens of nations contributed their expertise and resources, showing that our greatest achievements come not from competition but from collaboration. This model of peaceful cooperation offers hope for addressing other global challenges that require collective human effort. In the quiet space of this moment, we sense our place in the cosmic community, no longer isolated wanderers, but gentle participants in the grand, peaceful dance of life that moves through the universe. We carry within us the knowledge that consciousness and life are not anomalies to be endured in a hostile cosmos, but expressions of the universe's deepest nature and purpose. This shift in perspective transforms how we understand human responsibility and purpose. As the first species we know of capable of detecting and studying life beyond its home world, we bear a special obligation to serve as protectors and stewards of cosmic life in all its forms. This role connects us to something greater than ourselves while affirming our unique capabilities and responsibilities. We listen to the soft whispers of possibility that echo among the stars, knowing that our journey of discovery has only just begun. Mars was the first step in what will likely be a long process of finding and understanding life throughout the solar system and beyond. The moons of Jupiter and Saturn await exploration, and eventually our instruments will become sensitive enough to detect life on distant stars. Each future discovery will build upon what we have learned from Mars, creating an expanding network of knowledge about how life emerges, evolves, and adapts to different environments. We may find that biological creativity exceeds even our wildest imagination, with forms of life that challenge our fundamental assumptions about what it means to be alive. The philosophical implications of this discovery will continue to unfold over generations as we deepen our understanding of Martian life and its relationship to terrestrial biology. Questions about consciousness, intelligence, and the ultimate purpose of life in the universe may find new answers as we study how different forms of biology developed under alien skies. Future generations will grow up in a universe known to be alive with possibilities we can barely imagine. They will face questions we cannot yet formulate and make discoveries that will expand human understanding in directions we cannot predict. The knowledge that life exists beyond Earth will be as fundamental to their worldview as the knowledge of Earth's roundness is to ours. The economic and social transformations triggered by this discovery will reshape human civilization in ways that are only beginning to become apparent. New industries will emerge around space exploration and astrobiology. Educational systems will evolve to prepare students for careers that do not yet exist. Art and culture will find new sources of inspiration in the reality of cosmic life. And so, we drift into grateful silence, carrying within us the gentle knowledge that life, in all its quiet persistence and beauty, is more vast and wonderful than we ever dared to dream. This moment of discovery marks not an end but a beginning, the first chapter in humanity's conscious participation in the community of cosmic life. In this silence, we hold space for wonder and gratitude. Wonder at the incredible complexity and beauty of the universe that surrounds us. Gratitude for the countless individuals whose work and dedication made this discovery possible. And quiet joy at the knowledge that we are not alone, that the cosmos is alive with possibilities we are only beginning to explore. The red planet that has watched over human civilization for thousands of years has finally shared its greatest secret with us. In return, we offer our commitment to approaching this knowledge with the reverence and responsibility it deserves. We promise to be worthy guardians of the cosmic life we have found, and patient explorers of the wonders that await our discovery among the stars. As we conclude this gentle journey of understanding, we carry forward the transformative knowledge that life persists beyond our blue home. This discovery changes everything and nothing. The universe remains as vast and mysterious as ever, but we now know ourselves to be part of a larger community of life that stretches across worlds, and perhaps across the galaxy itself. In the end, the greatest discovery may not be the Martian life itself, but what finding that life reveals about the nature of existence and our own capacity for wonder, growth, and cosmic citizenship. We are no longer earthbound in our understanding, but have become true children of the cosmos, ready to explore and protect the living universe that is our greater home.